keep it short, and then we're going to do a sort of fireside chat Q&A with Diana. I actually have only been working on AI for about 6 years. Before that, had a long career, the vast majority of my career as a theoretical physicist working in academia. And so how did I get to AI? Well, I want to be brief. Why did I start in physics? It was basically because my mom was a science fiction writer, and I wanted to figure out if we could build a faster-than-light drive, and physics was the way to do that. I also was very excited about just understanding the universe. How do things work? How do the biggest trends that underlie sort of everything that we see around us, where does that all come from? For example, is the universe deterministic? Do we have free will? I was very, very interested in all of those questions. But fortunately, along the way, during my career as a physicist, I met a lot of very, very interesting, very deep people, including many of the founders of Anthropic that I now work with all of the time. And I was really interested in what they were doing, and I kept track of it. And as I moved from among different subject areas in physics, from Large Hadron Collider physics, particle physics, cosmology, string theory, and on, I got a little bit frustrated, a little bit bored. I didn't feel like we were making progress quickly enough. And a lot of my friends were telling me that AI was becoming a really big deal. And I didn't believe them. I was really skeptical. I thought, well, AI, people have been working on it for 50 years. SVMs aren't that exciting. That was all we knew about back in 2005, 2009 when I was in school. But I got convinced that maybe AI would be an exciting field to work on. And I got very lucky to know the right people, and the rest is history. So I'm going to talk a little bit about how our contemporary AI models work and how scaling is leading them to get better and better. So there are really two fundamental phases to the training of contemporary AI models like Claude, ChatGPT, et cetera. The first phase is pre-training. And that's where we train AI models to imitate human-written data, human-written text, and understand the correlations underlying that data. And these figures are very, very retro. This is actually from the playground of the original GPT-3 model. And you can see that as a speaker at a journal club, you're probably elephant me to say certain things. The word elephant in that sentence is really, really unlikely. What pre-training does is teach models what words are likely to follow other words in large corpora of text, and now, with contemporary models, multimodal data. The second phase of training for contemporary AI models is reinforcement learning. This is another very retro slide. It shows the original interface we used for sort of Claude 0 or Claude -1 back in the ancient days of 2022, when we were collecting feedback data. And what you see here is basically the interface for having a conversation with very, very early versions of Claude and picking which response from Claude was better according to you, according to crowd workers, et cetera. And using that signal, we optimize, we reinforce the behaviors that are chosen to be good, that are chosen to be helpful, honest, and harmless, and we discourage the behaviors that are bad. So really, all there is to training these models is learning to predict the next word and then doing reinforcement learning to learn to do useful tasks. And it turns out that there are scaling laws for both of these phases of training. So this is a figure that we made 5 or 6 years ago now. And it shows how, as you scale up the pre-training phase of AI, you predictably get better and better performance for our models. And this was something that came about because I was just sort of asking the dumbest possible question. As a physicist, that's what you're trained to do. You sort of look at the big picture and you ask really dumb things. I'd heard it was very popular in the 2010s to say that big data was important. And so I just wanted to know, how big should the data be? How important is it? How much does it help? Similarly, a lot of people were noticing that larger AI models performed better. And so we just asked the question, how much better do these models perform? And we got really lucky. We found that there's actually something very, very, very precise and surprising underlying AI training. This really blew us away, that there are these nice trends that are as precise as anything that you see in physics or astronomy. And these gave us a lot of conviction to believe that AI was just going to keep getting smarter and smarter in a very predictable way. Because as you can see in these figures, already back in 2019, we were looking across many, many, many orders of magnitude in compute, in data set size, in neural network size. And so we expected, once you see something is true over many, many, many orders of magnitude, you'd expect it's probably going to continue to be true for a long time further. So this has sort of been one of the fundamental things that I think underlies improvements in AI. The other is actually also something that started to appear quite a long time ago, though it's become really, really impactful in the last couple of years, is that you can see scaling laws in the reinforcement learning phase of AI training. So a researcher about 4 years ago decided to study scaling laws for AlphaGo, basically putting together two very, very high-profile AI successes, GPT-3 and scaling for pre-training, and AlphaGo. This was just a researcher, Andy Jones, working on his own with like his own, I think maybe single GPU back in these sort of ancient days. And so he couldn't study AlphaGo, that was expensive, but he could study a simpler game called Hex. So he made this plot that you see here. Now, ELO scores, I think, weren't as well known back then, but all ELO scores are, of course, is chess ratings. They basically describe how likely it is for one player to beat another in a game of chess. They're used now to benchmark AI models to see sort of how often does a human prefer one AI model to another. But back then, this is just sort of the classic application of ELO scores as chess ratings. And he looked at, as you train different models to play this game of Hex, which is a very simple board game, a bit simpler than Go, how do they do? And he saw these remarkable straight lines. So it's sort of a skill in science to notice very, very simple trends, and this was one. I think it went unnoticed. I think people didn't focus on this sort of kind of scaling behavior in RL soon enough, but eventually it came to pass. So we see that basically you can scale up the compute in both pre-training and RL and get better and better performance. And I think that's sort of the fundamental thing that is driving AI progress. It's not that AI researchers are really smart or they suddenly got smart. It's that we found a very, very simple way of making AI better systematically, and we're turning that crank. So what kinds of capabilities is this unlocking? I tend to think of AI capabilities on two axes. I think the less interesting axis, but it's still very important, is basically the flexibility of AI, the ability of AI to meet us where we are. So if you put, say, AlphaGo on this figure, it would be very, very far below the x-axis, because although AlphaGo was super intelligent, it was better than any Go player at playing Go, it was only able to operate in the universe of a Go board. But we've made steady progress since the advent of large language models, making AI that can deal with many, 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 all of the modalities that people can deal with. We don't have AI models, I think, that have a sense of smell, but that's probably coming. And so as you go up the y-axis here, you get to AI systems that can do more and more relevant things in the world. I think the more interesting axis, though, is sort of the x-axis here, which is how long it would take a person to do the kinds of tasks that AI models can do. And that's something that has been increasing steadily as we increase the capability of AI. This is sort of the time horizon for tasks. And an organization, Meter, studied this very systematically and found yet another scaling trend. They found that if you look at the length of tasks that AI models can do, it's doubling roughly every 7 months. And so what this means is that the increasing intelligence that is being baked into AI by scaling compute for pre-training and RL is leading to predictable, useful tasks that the AI models can do, including longer and longer horizon tasks. And so you can sort of speculate about where this is heading, and in AI 2027, folks did. And this kind of picture suggests that over the next few years, we may reach a point where AI models can do tasks that don't just take us minutes or hours, but days, weeks, months, years, et cetera. Eventually, we imagine AI models or millions of AI models perhaps working together will be able to do the work that whole human organizations can do. They'll be able to do the kind of work that the entire scientific community currently does. One of the nice things about math or theoretical physics is that you can make progress just by thinking. And so you can imagine AI systems working together to make the kind of progress that the theoretical physics community makes in say, 50 years in a matter of days, weeks, et cetera. So what is left, if this sort of picture of scaling can take us very far, what is left? I think that what may be left in order to unlock kind of human-level AI broadly construed is relatively simple. One of the most important ingredients, I think, is relevant organizational knowledge. So we need to train AI models that don't just greet you with a blank slate, but can learn to work within companies, organizations, governments, as though they have the kind of context that someone who's been working there for years has. So I think AI models need to be able to work with knowledge. They also need memory. What is memory if not knowledge? I distinguish it in the sense that as you do a task that takes you a very, very long time, you need to keep track of your progress on that specific task. You need to build relevant memories, and you need to be able to use them. And that's something that we've begun to build into Claude 4, and I think will become increasingly important. A third ingredient that I think that we need to get better at, and we're making progress on, is oversight. The ability of AI models to understand sort of fine-grained nuances, to solve hard, fuzzy tasks. So it's easy right now, and you see an explosion of progress, for us to train AI models that can, say, write code that passes tests, or that answer math questions correctly, because it's very crisp what's correct and what's incorrect. So it's very easy to apply reinforcement learning to make AI models do better and better at those kinds of tasks. But what we need and are developing are AI models that help us to generate much more nuanced reward signals so that we can leverage reinforcement learning to do things like tell good jokes, write good poems, and have good taste in research. The other ingredients that we need, I think, are simpler. We obviously need to be able to train AI models to do more and more complex tasks. We need to work our way up the y-axis from text models to multimodal models to robotics. And I expect that over the next few years, we'll see increasing continued gains from scale when applied to these different domains. And so how should we sort of prepare for this future, these possibilities? I think there are a few things that I always recommend. One is, I think it's really a good idea to build things that don't quite work yet. This is probably always a good idea. We always want to have ambition. But I think specifically, AI models right now are getting better very, very quickly, and I think that's going to continue. That means that if you build a product that doesn't quite work because Claude 4 is still a little bit too dumb, you can expect that there will be a Claude 5 coming that will make that product work and deliver a lot of value. So I think that's something that I always recommend, is sort of experiment on the boundaries of what AI can do, because those boundaries are moving rapidly. The next point, I think, is that AI is going to be helpful for integrating AI. I think that one of the main bottlenecks for AI is really just that it's developing so quickly that we haven't had time to integrate it into products, companies, other things, everything else that we do into science. And so I think that in order to sort of speed that process up, I think leveraging AI for AI integration is going to be very valuable. And then finally, I mean, I think this is sort of obvious for this crowd, but I think figuring out where adoption of AI could happen very, very quickly is key. we're seeing an explosion of AI integration for coding. And there are a lot of reasons why software engineering is a great place for AI. But I think the big question is sort of what's next? What beyond software engineering can grow that quickly? I don't know the answer, of course, but hopefully you guys will figure it out. So that's it for the talk. I want to invite Diana on stage for a chat.
YC's next batch is now taking applications. Got a startup in you? Apply at ycombinator.com/apply. It's never too early, and filling out the app will level up your idea. Okay, back to the video.
That was an awesome talk about all the scaling laws. And recently, Anthropic just launched Claude 4, which is just available. Curious, how does it change what is possible as all these model releases keep compounding for the next 12 months?
I think that we'll be in trouble if it's 12 months before an even better model comes out. But I guess a few things with Claude 4. I think that with Claude 3.7 Sonnet, it was already really exciting to use 3.7 for coding. But I think something that everyone noticed was that 3.7 was a little bit too eager. Sometimes it just really wanted to make your tests pass, and it would do things that you don't really want. There are a lot of like try excepts, things like that. So with Claude 4, I think that we've been able to improve the model's ability to act as an agent specifically for coding, but in a lot of other ways, for search, for all kinds of other applications. But also improve its supervision, the sort of oversight that I mentioned in my talk, so that it follows your directions and hopefully improves in code quality. I think the other thing that we've worked on is improving its ability to save and store memories. And we hope to see people leveraging that, because Claude 4 can blow through its context window with a very complex task, but can also store memories as files or records, retrieve them in order to sort of keep doing work across many, many, many context windows. But I guess finally, I think that the picture that scaling laws paint is one of incremental progress. And so I think that what you'll see with Claude is that steadily it gets better in lots of different ways with each release. But I think that scaling really suggests a kind of smooth curve towards what I expect is kind of human-level AI or AGI.
Is there some special feature that a lot of the audience here are going to get excited? Some beta that you can, some alpha leak you can give everyone on what you think people are going to fall in love with the new APIs?
I think the thing that I'm most excited about is sort of memory unlocking longer and longer horizon tasks. I think that like as time goes on, we're going to see Claude as a collaborator that can sort of take on larger and larger chunks of work.
This is to your point of all these future models being able to take bigger and bigger tasks right now. At this point, they're able to do tasks in the hours?
Yeah, I think so. I think it's a very imprecise measure, but I think that right now, if you look at sort of software engineering tasks, I think Meter literally benchmarked how long it would take people to do various tasks, and yeah, I think it's a time scale of hours. I think just like broadly as people work with AI, I think that the people who are skeptics of AI will say correctly that AI makes lots of stupid mistakes. It can do things that are absolutely brilliant and surprise you, but it can also make basic errors. I think one of the sort of basic features of AI that's different about the shape of AI intelligence compared to human intelligence is that there are a lot of things that I can't do, but I can at least judge whether they were done correctly. I think for AI, the judgment versus the generative capability is much closer, which means that I think that a major role people can play in interacting with AI is kind of as managers to sort of sanity check the work.
Which is fascinating, because one of the things we